In this video, we're going to take a look at how temperature changes affect a system that's at equilibrium. So here we have a system in equilibrium, and as you notice, this system is an endothermic system going from left to right because the energy is there. This is the delta H is on the reactant side or on the left side, so it's endothermic. As we learned, the stresses involved the temperature change affect the system differently depending on whether it's endothermic or exothermic. So here we're going to model endothermic. You can try practice problems or you model exothermic later. So we're going to start off by just establishing an initial equilibrium. We'll put in some H2, some O2, and initially there's no product, and we're going to go ahead and throw in the H2 and O2 and then let the reaction happen until equilibrium is reached. So we'll start off with 0 H2Os. And over time, that's going to be produced. And then it's in a flat line. And this change will be a change of plus 2x. And for the reactants, I'm going to start them at two different areas. But here I have my H2. Here I have my O2. So my reactants will be used up until they essentially flatline. And you will notice that this should have probably been more pronounced, but this represents minus 2x, and this represents minus 1x, because the H2s use up twice as fast as the O2 due to the coefficient of 2 here and coefficient of 1 here. And this is produced twice as fast as the O2 being used up, but the same rate as the H2O. So this is our H2, this is our O2, and this is our H2 over here. And so equilibrium has been reached once everything has essentially flatlined. So things stop changing. This is our equilibrium. And so now we're going to add a stress to our equilibrium system. Let's do something like this. Let's increase the temperature. So if our stress is increasing the temperature, we are basically adding heat or energy. So we've added a lot of heat, and the heat's on this side here. So we want to get rid of the heat on that side, because now think of it like a reactant. We've added more reactant essentially. So to undo, we need to lower the heat. To undo, lower heat on the reactant side there. So how do we do that? Well, we need to use up that energy. We need to use it up in our reaction. So we need to shift right. For an endothermic reaction, when you increase the temperature, you need to shift the reaction right to use up that energy that's on that that's in the reactant side. So we're essentially going this way here. And we're going to be using up H2 and O2 and producing more H2O. So let's go ahead and do that. And it's not going to be a sharp decrease and a sharp increase because we didn't add anything. We're just changing the energy there. So this will drop. This will drop as well, just not as much. And this one here will go up. If I had numbered everything, it would be easier to make this more consistent, but essentially this has dropped by minus 2x. This has dropped by minus x. And this here has gone up by plus 2x because of the coefficients again. And then until equilibrium is reached again. And so now we have our new equilibrium where everything is once again stopped changing or flatlined. Okay, so this is our new equilibrium. And remember that when you change temperatures, temperatures change the equilibrium constant. So a temperature change is really the only thing that's going to change the temperature, the equilibrium constant. So we have a new K, whereas previously when we changed molarity, we did not have a new K. All the Ks were the same once equilibrium was reestablished. Here, now we have a new K value. And so we increased our temperature. It definitely increased the rate of the forward reaction a lot more than the reverse reaction. And so that's why we have a new K value now, since energies are in different positions when it comes to the reverse and the forward reaction. So essentially going one way, you're endothermic, but going the other way, you're exothermic, so the temperature affects you differently. So there we've added a stress, we added heat. Let's take a look at what happens if we remove heat, if we lower the temperature. So now, our system was happy at equilibrium and everything, but now we're going to go and stress it again just to see what happens. So we're going to lower the temperature. We're going to remove heat. And so we need to undo this somehow. So we somehow need to undo this. So to undo, we need to increase heat. We removed some heat. So we need to increase heat on the side that lost heat. And so we lost heat over here because we lowered the temperature. So we need to make more heat. So in other words, I need to go from the right side to the left side. I need to break down some water to produce H2 and O2, but also to release some energy so I can get some heat back there since I removed so much there. So we're going to shift left. So what we're going to do now is if we're shifting left, we're using up O2. We're using up O2. So that will drop and stabilize. And this will be minus 2x. And we're producing H2 and O2. So this will go up and stabilize. And this will also go up and stabilize. And so this went up by plus 2x, and this went up by plus x. Roughly. It really depends on how much heat we removed or added. So it's a whatever what essentially it's the ratios compared to each other. So if H2 went up 4 moles, then O2 only went up 2 moles. Okay, so I'm just putting X there because I'm not sure how much they went up. I didn't put any specific numbers there. So now we have a new equilibrium established. I'm just going to use a different color so when everything stopped changing. New equilibrium with a new K again because we lowered the temperature. So in this graphing activity, what we did is we took a system that was endothermic and we added stress to it. And the stress could have been increasing temperature or lowering temperature. We want to see what shift that would cause based on the fact that it's endothermic. We also saw that this is a little bit different from, different in many ways from adding reactants or removing products or adding product. The K values when the equilibrium is reestablished will be different from one another, whereas over here, they're all the same when equilibrium is reestablished. And also, we don't see any sharp increase or sharp decreases. It's all gradual consumption or using up and gradual production or forming. Whereas here, you do see at least one of them, whatever one you added or removed, has a sharp increase for adding, sharp decrease for removing, and then the gradual takes place after. The other ones are just gradual if you haven't added any. They're just going with the process of the reaction. So this video we saw temperature changes, how they affect equilibrium. In other worksheets and samples, you're going to try to do this for exothermic reactions and see what the stress would look like. And you'll see in some of the activities, you'll have numbers associated there, so you can actually go in and calculate the equilibrium constant using those numbers. In the next video, we're going to take a look at volume changes and pressure changes and how they affect a system, causing them to shift. So just pay attention to how the K value will be the same in this one as well.